നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ പറഞ്ഞിട്ടുണ്ടായിരുന്നു നമ്മൾ ക്വാണ്ടം മെക്കാനിക്സ് പറയുമ്പോൾ we have to think about the Hilbert space. അപ്പോൾ എന്താണ് Hilbert space? We do all the operations in quantum mechanics in Hilbert space. So what is Hilbert space? So Hilbert space consists of a set of vectors as we have seen in the linear vector space, psi, phi, chi, and a set of scalars a, b, c. We have already seen in the linear vector space, and these vectors and scalars satisfy the following four properties. If these vectors and scalars satisfying the following four properties, then that vectors and scalars consist of a space, that the space consists of these vectors and scalars known as Hilbert space. നമുക്ക് Hilbert space കുറിച്ച് പറയാം. Hilbert space H, it is represented by this H, and is a linear space, linear vector space. So Hilbert space is also a linear vector space, but it has some other properties, and therefore the properties of a linear space were considered, and it will have all the properties of a linear vector space. Then Hilbert space is defined as a defined scalar product that is strictly positive. ഇവിടുത്തെ പ്രധാന പ്രോപ്പർട്ടി എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ദ സ്കെയിലാർ പ്രോഡക്റ്റ് ദാറ്റ് ഇസ് സ്ട്രിക്ട്ലി പോസിറ്റീവ്. ഉദാഹരണമായിട്ട് നമ്മൾ ലീനിയർ വെക്ടർ സ്പേസിൽ -a വെക്ടർ ഇൻറ്റു +a വെക്ടർ we will get a -ab vector, right? But here in the Hilbert space we will always get a positive vector, the scalar product. The scalar product of an element psi with another element phi is in general a complex number denoted by this inner product psi phi, where psi phi is a complex number. The quantity psi phi is generally not equal to inner product phi psi. Therefore we can write psi phi equal to psi star phi, while phi psi inner product phi psi is equal to phi star psi. In the order ശ്രദ്ധിക്കുക. And the scalar product satisfy the following properties. The scalar product of psi with phi is equal to the complex conjugate of the scalar product of phi with psi. The scalar product psi phi is equal to phi psi star. This is the star represents the complex conjugate. The scalar product of phi with psi is linear with respect to the second factor if psi equal to a psi 1 plus b psi 2. അപ്പോൾ എന്താണ് ഹിൽബർട്ട് സ്പേസ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ you have to tell all these things, these properties a, b, c. അപ്പോൾ Hilbert space is a linear vector space and it has a defined scalar product, or the scalar product in the Hilbert space is strictly positive, and Hilbert space is separable and which is complete. ഇതാണ് അതിന്റെ ഡെഫിനിഷൻ. അപ്പോൾ നമുക്ക് the scalar product is linear. നമുക്ക് നോക്കാം. Product of scalar product phi a psi 1 plus b psi 2 equal to a into inner product phi psi 1 plus b phi psi 2, and anti-linear with respect to the first factor if phi equal to a phi 1 plus b phi 2. So product inner product scalar product a phi 1 plus b phi 2 comma psi equal to a star. This is the complex conjugate. So if the number comes out of the bracket, then it becomes the complex conjugate. A star phi 1 psi plus b star phi 2 psi. അപ്പോൾ ഈ ഓർഡർ നല്ലോണം നിങ്ങൾ ശ്രദ്ധിക്കുക. അതായത് this is the property of Hilbert space. And the scalar product of a vector psi with itself is a positive real number. Scalar product with itself is a positive real number. That is scalar product of psi equal to psi square, which is greater than or equal to 0. Where the equality holds only for psi equal to 0. Then H is separable. There exists a Cauchy sequence psi n belongs to Hilbert space. That means there are n number of psi vectors such that for every psi of H, that is every psi of the Hilbert space, and a positive number epsilon greater than 0, there exists at least one psi n of the sequence for which psi minus psi n is less than epsilon. That means we can separate the vectors. Then H is complete. Every Cauchy sequence psi n belongs to H converges to an element of H. That is, for any psi n, the relation limit nm tends to infinity, psi n minus psi m equal to 0. Defines a unique limit psi of H such that limit n tends to infinity, psi minus psi n equal to 0. നമുക്കൊരു വീഡിയോ നമുക്ക് നോക്കാം. നിങ്ങൾക്ക് കൂടുതലായിട്ട് നിങ്ങൾക്ക് മനസ്സിലാക്കാൻ പറ്റും എന്താണ് ഹിൽബർട്ട് സ്പേസ്. നിങ്ങൾ ഹിൽബർട്ട് സ്പേസിനെ ഡിഫൈൻ ചെയ്യുമ്പോൾ വാട്ട് ഈസ് ആൻ ഹിൽബർട്ട് സ്പേസ്, നിങ്ങൾ ഇത്രയും കാര്യങ്ങൾ. ഹിൽബർട്ട് സ്പേസ് ഈസ് എ ലീനിയർ വെക്റ്റർ സ്പേസ് which is separable, which is complete, and the inner product is strictly positive. എന്നിട്ട് ഇത്രയും കാര്യങ്ങൾ നിങ്ങൾ എഴുതേണ്ടതായിട്ട് വരും. നമുക്ക് വീഡിയോയിലേക്ക് പോകാം.
In this video, we're going to be looking at a specific kind of vector space known as a Hilbert space. What a Hilbert space is it's a special kind of vector space. It has all the properties that a regular vector space has, and it has a few more additional properties also. One of these additional properties is that a Hilbert space, in addition to the vector addition and the scalar multiplication operation, also has an inner product operation. What do I mean by inner product? An inner product is an operation that takes two vectors and spits out a scalar. Now, for a vector space like a Hilbert space to have a valid inner product, we need this operation to obey certain constraints. One of these is conjugate symmetry. What this means is that the inner product of two elements in the Hilbert space is the complex conjugate of the inner product of the two elements, but now in the opposite order. So the inner product isn't commutative, but it's conjugate symmetric. The other property is linearity with respect to the second vector. So if I'm taking the inner product between psi1 and a second vector that includes the scalars a and b come out unchanged in the resulting inner product. However, if the scalars a and b appear in the first vector, we have to take the complex conjugates of those scalars when we pull them out of the inner product. In addition, the inner product of a vector with itself must not be negative, and is only 0 when the vector itself is 0. This is also known as positive definiteness. Finally, how close two vectors are in Hilbert space is defined according to the distance formula, which is expressed in terms of the inner product. Now, this closeness relation or distance formula comes in handy for a later property, which we'll get to soon. Hilbert spaces are also separable, which means they contain a countable dense subset. These are some pretty hardcore math terms, but I'll try to explain them informally to give you an intuition. For example, the set of real numbers is separable because its countable dense subset is the set of rational numbers Q. Q is countable because it consists of all numbers that can be expressed as ratios between two integers. Since integers are countable, 1, 2, 3, 4, it follows that their ratios are also countable. I'll have to count to infinity to count all rational numbers, but I can still count them because they're ratios of two integers. This is in contrast to irrational numbers, which can't be expressed in terms of integers and are uncountable. The set of rational numbers Q is also a dense subset because any real number is either a rational number or we can make a real number arbitrarily close to a rational number. Even irrational numbers like pi can be written as a sequence of rational numbers of increasing precision, like 3.1, 3.14, 3.142, and so on. Within this sequence, I can find a member that's as close to the actual value of pi as I want, and all of these members are rational numbers because they're expressed in terms of decimals that end at a certain point and don't continue to infinity. Now, because the set of rational numbers is a subset of the set of real numbers, and because it's countable and dense, we say that the set of real numbers is separable. Because the set of real numbers is separable, we can consider the set of real numbers to be a Hilbert space, because in addition to being separable, it's also a vector space, and it also has that inner product operation that you probably know as the dot product. For a general Hilbert space, however, a countable subset S containing the vectors phi n means that I can count the number of elements in that subset, while a dense subset is one so that every element in the Hilbert space is either a member of that subset, S, or can be made arbitrarily close to one, where closeness is determined according to this distance formula I mentioned above. It should be noted that the property of separability isn't always used in the definition of Hilbert spaces. Instead, it's occasionally assumed that a Hilbert space is separable. But some books mention separability as a specific property of Hilbert spaces. The last property of Hilbert spaces is that they're complete, and formally this means that there aren't any gaps. Formally, this means that every Cauchy sequence, or a sequence in which two members of the sequence get arbitrarily close to each other as we go further down the sequence, every Cauchy sequence converges to an element phi in the Hilbert space. For example, the set of rational numbers is incomplete since there are gaps between the rational numbers that are occupied by irrational numbers. However, the set of real numbers, which consists of both rational and irrational numbers, is complete because it has no gaps. So in the end, a Hilbert space is a set which satisfies all four of these properties, being a linear vector space, having a valid inner product, being separable, and being complete. Anyway, that does it for this video. In the next video, we're going to talk about some types of Hilbert spaces, specifically the ones we care about in quantum
ഒരു വീഡിയോ
mechanics.
കൂടി നമുക്ക് കണ്ടിട്ട് നമുക്ക് ഈ വീഡിയോ അവസാനിപ്പിക്കാം. Have you ever been?
First off, every first-year student knows about vectors in the plane. In particular, each vector in the plane has two coordinates,
Grammarly
x1, x2.
does more than catch errors.
Another vector y has coordinates
With Grammarly,
y1, y2.
you can find really good,
Define
perfect.
the dot product in this way, and we can define the length of the vector, sometimes called the norm, by this way, which is the sum of the squares of the coordinates. Now, Hilbert space is a generalization of this idea from 2 dimensions to infinity of dimensions. So in particular, instead of having a vector x1, x2, no longer in the plane, it's an infinite number of coordinates, all the way out to infinity. And of course, the y1, y2 has coordinates all the way out to infinity. Now the dot product, of course, has to sum all of these out to infinity, and the length has to be summed all the way out to infinity, and we have the condition that the sum of the squares of all the coordinates has to be bounded, or it's less than infinity. Ordered systems of numbers which satisfy these two properties are called Hilbert spaces. They're named Hilbert spaces in honor of David Hilbert, a famous professor of Göttingen at the beginning of the 20th century, and who invented Hilbert spaces, which were immediately used thereafter by Schrödinger and other people to describe problems in quantum mechanics. In particular, if you wish to study the solution of Schrödinger's equation, the so-called wave function, you need to understand what a Hilbert space is and to study this in the context of Hilbert space. And so Hilbert spaces are basic these days, not only to mathematics, but also to physics, not only quantum physics, but many other areas of physics.
Okay, thank you.